The first arithmetic operation we are going to explore is the addition of two n-bit unsigned integers. Specifically, we want to understand how to implement an adder. To do so, we first need to analyze how binary addition works. Adding two unsigned integer values involves summing corresponding pairs of bits, starting from the rightmost least significant bit and propagating the carry when necessary. Let's walk through the basic rules of binary addition. 0 plus 0 equals 0, with carry 0. 0 plus 1 and 1 plus 0 both equal 1, with carry 0. 1 plus 1 equals 0, with carry 1. By applying these rules to each bit of the two operands, we can build a basic unit, that is a one-bit adder, and then replicate it n times to construct a modular adder. This kind of arithmetic circuit is referred to as bit slice, since it is composed of repeated slices, one for each bit. Based on the rules we've just reviewed, we can now define the basic module called the one-bit adder, which we will refer to as the half adder. This one-bit adder has two inputs, x and y, and two outputs, s, which represents the sum, c, which represents the carry. The figure shows the truth table of the half adder, filled according to the binary addition rules we discussed earlier, along with its implementation using just two logic gates. The sum s is calculated as x XOR y. The carry c is calculated as x and y. This simple circuit forms the foundational building block for more complex n-bit arithmetic units, which we will explore in this video and in the following ones. To build an adder with n bits at each position I, we actually need not only to generate the corresponding sum and the carry out, but also to manage the carry produced by the previous position I minus 1. Therefore, the module in position I receives as inputs the bits xi and yi, along with the carry in ci from the previous module, and it must produce the sum si and the carry ci plus 1 to propagate to the next module. This module, which includes the additional input for the incoming carry, is called a full adder. The figure below shows the truth table for the full adder and its equivalent circuit, composed of two half adders and one OR gate. The truth table shows that the sum output is 1 when the number of ones on the three inputs is odd, that is 1 or 3. For the carry output, it is 1 when at least two ones are present at the inputs, that is 2 or 3. Starting from the truth table, we can derive the equivalent logic circuits used to compute the sum output Si and the carry out signal Ci plus 1. In both cases, we observe that each output can be generated with a latency of 2 logic levels. In the bottom right corner, we see an example of a graphical representation of a full adder module. Do note that, although standard circuit representations often follow a left-to-right or top-to-bottom layout for module inputs, with full adders and more generally in arithmetic architectures, it is not uncommon to find representations where the output signals propagate to the left. This is primarily due to the carry signals propagating toward the most significant bits. The complete adder obtained by connecting all the modules is called ripple carry adder or carry propagation adder because the modules form a chain linked by their carry signals. It is important to note that this architecture is regular and reuses identical modules. The first module, at position 0, could in principle be implemented using a half adder rather than a full adder, with the input C0 equals 0. However, we will see later that this module is usually kept as a full adder because the carry C0 can be used for computations in 2's complement. The addition of two n-bit numbers requires a time approximately equal to n times the delay of a single adder module. More precisely, if we define Ts as the delay of the sum computation and Tr as the delay for carry computation, then the latency required to obtain all the sum bits in an n-bit operation is n minus 1, multiplied by the carry computation time Tr plus 1 sum time Ts, where Ts is the delay to sum the most significant bits. At a higher level of abstraction, we can view the ripple carry approach also in terms of adders with n bits. In fact, by considering an n-bit ripple carry adder as a basic block, we can build an adder with n multiplied by k bits by connecting k adders with n bits in a chain through their carry signals. The adder structured in this way is the one shown in the lower part of the slide. It is also known as the ripple carry block architecture or block-based ripple carry adder.